when you do modular calculation, sometimes we have different result than usual. For instance, if we solve the problem like this without any moduli or modulus, we just get the solution such as these. And these are the only possible solutions in general. But when you use this modular calculation, it's not necessarily true. For instance, x squared equals 1 is the case. Then, for instance, of course, these works. But will these be the only solutions? No. In addition to these, for instance, 3 will work, right? And 5 will work. Why? 3 squared is 9. 9 o'clock and 1 o'clock are the same, right? 5 squared is 25. 25 o'clock and 1 o'clock are the same. That means we cannot say that the solution to this quadratic equation has just 2 solutions, right? In this case, just 2 solutions, right? Just 2. But here, take a look. 1, 3, 5, and minus 1. Minus 1, if we don't use minus sign, then 1 and 7, right? So already 4 solutions. So there is no guarantee. So on the exam, if you just cancel out and say that x equals plus 2 and minus 1, it's not absolutely correct, right? It's not correct. You should let me know the reason. So I will state this thing. X squared equals 1 with mod p prime, right? Where p is prime. Then how many solutions can we expect? And what are the solutions? Of course, 1 and negative 1. 1 and negative 1 are obvious solutions. But are they all? So let's investigate this problem. So we rewrite the problem using this. Then this is equivalent to saying what? X squared minus 1 is divided by what? This is equivalent to saying the prime number p, right? Any questions? And we can factor the right side, then p plus x plus 1 and x minus 1. X plus 1 and x minus 1. And from this, we say that p divides x plus 1 or x minus 1, right? From the theorem that I proved before, p divides x plus 1 or x minus 1. That means if we translate this using modular relation, x is what? Negative 1 or x is 1 mod p. So I use the theorem that I proved before. If prime divides product, then it should divide some factor, right? If prime divides some product, then it divides some factor. If it's not prime, it's not true. But if it's prime, it's true. I proved this before. If you want to know the place that you can find this fact, ask me. Then I will let you know. But you already know, right? If prime divides product, then it should divide some factor in the product, right? Either this one or this one. If this one, then you get this fact by just equivalent writing, right? And then this, and this. That means these are the only solutions. Can you get other solutions than these? Impossible, right? Impossible. So when it is prime, and when you have x squared equals 1, then there are only 2 possible solutions. Or, of course, minus 1 and p minus 1 are the same. So among factors such as these, 1 through p minus 1, only 2 numbers has the property that 1 squared is 1, yes, right? And then p minus 1 squared is 1, right? So only 2 numbers satisfy this, and other numbers in between do not satisfy us. In other words, between 2 through p minus 2, we cannot find any number satisfying this condition. These numbers cannot satisfy this condition. If you don't agree with me, ask me. So between 2 through p minus 2, there is no chance that we will get x squared equals 1. Only way is 1 or negative 1. In other words, p minus 1. Only there are two possible ways. Other than these two, other numbers in between cannot satisfy. So this is the key to the proof of Wilson's theorem. So if you don't have any objection, I will continue. But if you have a doubt about this proof, ask me. Then now I will do it. So my claim, I will write the claim, right? My claim is this. If you multiply for the prime number p, 2, 3, and all the way up to p minus 2, then it should be congruent to 1 mod p. This is my claim. And I will prove this. By proving this, I'm proving Wilson's theorem, because Wilson's theorem is this one multiplied by p minus 1, the last number, right? Then p minus 1 multiplied to both sides. Then left side is product of 1 through p minus 1. The right side is 1 times p minus 1. P minus 1 is congruent to negative 1, right? So it's the proof of the Wilson theorem. So Wilson's theorem is essentially this one. But check this. It's amazing. Why? Pick any prime number. You may pick any prime number. So I will use MATLAB. So you can pick prime. For instance, 13. So n equals 13. Do you get it? Then I can create 2 through n minus 2, right? Or I will say p equals n, right? P equals n. And then I will pick 2 through p minus 2. So I created these numbers, right? 2 through 11. Then if you multiply all these numbers, it is 1. Isn't it amazing? So let's do it. So I will multiply all these numbers, and then I get this number. And then I calculate the mod of this number, 1. Right? Pick any prime, big or small, pick any prime. Then multiply 2 through p minus 2. Then you will always get 1. So one more time, I will do it. So p equals 17, right? Then 2 through p minus 2, 2 through p minus 2 is 2, 3, 4, and this. And I multiply all these numbers, right? I multiply all these numbers. And then after multiplying this, I calculate the mod of this number. 1. So no matter what prime you pick, you will get this result. In other words, in mathematics, we are not interested in investigating this by computer program or by trying up to some prime. For instance, I calculated this up to 100th prime or 1000th prime. No. In mathematics, we want to prove for all cases. Do you get it? So this is the difference between computer and human intelligence. So human found this fact and then proved it. Then afterwards, we don't have to verify this in our program. We can just use this fact to create better algorithm or short circuit. So as you can see, what I will do is this one. Pick generic number A. Pick generic number A. Then, because P is prime, this A is relatively prime to P. Do you get it? This A cannot be A cannot have GCD greater than 1. No matter what A we pick in between, this A is relatively prime to P. So consider this Diophantine equation or just modular equation. Then, because GCD of A and P is 1, it has a solution. Do you get it? it has a solution, and I call this X inverse. In other words, if we pick A, so if we pick A, then we can find some number A prime. That A prime is some number between 2 through P minus 2. That is the one that I will show. But first of all, will there be a chance that these two numbers are the same or not? Will there be a chance that these two numbers could be the same or not? Any chance? You doubt, right? The previous column, what I showed you was this thing. If we satisfy x squared equals 1 with mod p, then there are only two possible solutions. By this fact, 1, negative or 1, right? There are only two ways. And I exclude these two numbers, right? 1 and p minus 1. So any other number than 1 and p minus 1 is impossible by the previous fact. Do you get it? So there is no chance. In other words, there is no chance that the inverse of arbitrary chosen number or generic A cannot be, right? There is no chance that this can be same. No chance. So they are different. Do you get it? They are different. Then, the second thing is this one. Can these be 1 or p minus 1 or 0? So take a look. For any generic way, A prime is not A, not 1, not p minus 1 or 0. All these are impossible. Do you get it? A prime cannot be A. Because it's A, then the previous result was wrong, right? If it is 1 or p minus 1, these are all excluded, right? These are all excluded. In other words, if A prime is 1, then the other is also 1. Because of the previous fact, right? So previous fact verifies three cases, and if it is 0, then 0 times A cannot be 1, 0. So there is no chance that A prime is this number. Then what happens? It must be some other number in between, right? So A prime is some other number in between. So initially we had 2 through p minus 2, total p minus 3 numbers. But now we reduce 2 numbers from this set. And then we do the same thing by picking the next number. Because I exclude some number here, and then some number here, we have a smaller set. And then next time I pick some other number, and then do the same thing. In this way, we can track down all these things, and by the property here, always this thing exists, right? This thing always exists, yes? Not necessary. We don't know. It is generic. For instance, depending on problem, for instance, if you have 7, and then A is 4, right? If 7 and A is 4, then A prime is 2, right? 4 times 2. So it is very generic. We are not handling a specific case. We are handling a very generic case. So what you do is, considering the set, and then reducing the size of the set each time, right, by 2, right? Then we can eventually handle all the numbers. And there is no repetition, redundancy, there is no. So this is done. So by repeating this process, we can find distinct pairs satisfying A prime is congruent to 1. Then take a look. There is an even number of numbers, right? There is an even number of numbers between 2 through p minus 2. And then each time we can cancel out 2, 2, 2. But there is no chance that the numbers are overlapped. There is no chance. If it's overlapped, then it satisfies the previous condition. It's impossible, right? So no overlapping possible. So we can cover all the numbers this way. Thus, if we rearrange this thing, then P through P minus 2 is congruent to 1. Done. So if you have a question or doubt, ask me.
You have an even number of numbers.
P is when P is greater than 3, right? We handled P less than or equal to 3 last time, right? So if P is greater than 3,
So P's going to be odd.
P is prime greater than 3, right? P is a prime number.
Odd. You subtract 2 from it, you still get an odd number.
We didn't start from 1. We start from 2. Any other questions? So this is the theorem. And the next thing is question about this case. We now know that x squared is congruent to 1, has 1 or negative 1 when the modulus is prime, right? We know this fact. Now, what about this question? What about this question? Will there even be a solution? And that's the question, right? First of all, will there even be a solution? If solution exists, what is it? So there are two questions. So people investigated this problem and concluded that solution exists if P is (4k plus 1 type), right? 4k plus 1 type. In other words, if it is pk plus 1 type, there is always a solution. So let's pick some number. For instance, 17. When you have 17, then 4 squared is what? 16, right? 16 plus 1 equals 17, right? So there is a solution. Do you get it? So when you have 16, then 4 squared 16, 16 o'clock is negative 1 o'clock, right? The same. So 17 is 4k plus 1 type. 13, is it 4k plus 1 type? Right? 4 times 3 plus 1. So 4k plus 1 type, then it has a solution. So find it. What number satisfies this condition? Something giving us 12, right? What gives us 12? So let's find it. What gives us 12? Like 25 squared, right? 5 squared is 25. 25 is congruent to 12, right? And then congruent to negative 1. Do you get it? We can reduce this prime. We can add this prime or subtract prime at will, right? In this modulus calculation. Modular calculation, we can subtract 13 or add 13, do anything, right? So we have the solution. So what I want to do now is not just finding solutions like this, because there are infinitely many prime numbers. We cannot do this with just examples. I want to prove it. So first of all, I will prove this case. If solution exists, then P is 4k plus 1. So this is the one I will prove. If solution exists, right? If a solution exists, then P is 4k plus. Because I said solution exists, let's say the solution, right? Let's say the solution is A, right? Because solution is, I call it A. You can call it anything, S, K, anything, right? Just solution. Then because it's a solution, A squared is congruent to negative 1 mod P. Do you get it? Then consider this, A P minus 1. What is it? You learned this thing last time. Very big thing last time. What is it? 1. It is called Fermat theorem, right? Fermat theorem. I used many different numbers in MATLAB and showed these things, right? No matter what A you pick, if it's not 0, then A to the power of P minus 1 is congruent to 1 mod P. Fermat theorem. And then now I use this thing and then check it. A squared, because P is odd, right? Because P is odd. Odd minus 1 is even. Even divided 2 is still integer, right? Do you get it? This is an integer. So A squared and some integer power. And as you can see, this is equal to negative 1 by this assumption, right? And then power of P minus 1. If you don't get it, ask me. I used the fact that A is a solution, right? So A squared is here to the power of this thing, which is an integer, gives us this result. Assume that P is congruent to P is the type 4k plus 3. So the odd number could be 4k plus 1 or 4k plus 3. Do you get it? Odd number could be 4k plus 1 or 3. Right? 1 or 3. So if this happens, then what can you say? If this happens, then this continues to be minus 1 and then 2 to the power of 4k plus 3 minus 1, then minus 1 to the power of 2k plus 1 after canceling out 2. What is the power of minus 1 to the power of even number? 1. So it is negative 1. Do you get it? So if P is 4k plus 3, it is negative 1. Then what happens? If this negative 1 is the right side, and then by this fact, this is congruent to what? Because of this fact, if we multiply, cancel out 2, by this fact it is what? 1. Do you get it? 1 is congruent to negative 1, right? 1 is congruent to negative 1 under this assumption, right? So if this happens, then 1 is congruent to negative 1 mod P. What does this mean? It means P divides the difference, right? P divides the difference. Can this happen? P is an odd prime. Can this happen? So a contradiction, right? A contradiction. In other words, my assumption here is wrong, right? This is the wrong assumption, right? Because of this wrong assumption, I got a strange result. So now I proved it by contradiction. Do you get it? If P happened to be 4k plus 3, then we will get a contradiction. In other words, P should be 4k plus 1. So I proved this direction. And I will prove the other direction. So because I don't have enough space, I will borrow the second column. Because of this region, P should be 4k plus 1, or in short, P is 1 mod 4, right? If we divide this, then mod 4, right? 4 here and then 4 here. So P should be this pattern. P is odd prime. Odd prime should have this effect. Now the other direction will be proved, and then I will consider a few other cases and then go to the next chapter. But before continuing, if you have a question, ask me. I will prove the other direction. If P is 4k plus 1, then a solution exists, right? A solution exists right? Solution to this case exists, right? Solution to this case exists. So this is the one that I will prove. And this proof is constructive. I will show you what the solution is. I'm just saying solution exists, but I will show you what the solution is. So to do it, I will use this fact. So because P is this, I multiply every number 1 through P minus 1. So 1, 2, 3, all the way up to P minus 1 and then half. And then next step is P plus 1 over 2, and then all the way up to P minus 1. And then as you can see, if we subtract, we have how many numbers here? It is 2k, right? And then this is 2k. Because there is total 4k plus 1. Do you get it? So there are 2k numbers in this column, and there are 2k numbers in this column if we break in half. Right? If we break in half, we have 2k numbers here, 2k numbers here, and then we get this result. Then I pair differently. I pair this way. Then if I multiply this thing, then it is, this product is congruent to negative 1 squared. Do you get it? 1 multiplied by P, we can remove P then. 1 multiplied by negative 1 is negative 1 squared. And if I multiply this number, then it is congruent to negative 2 squared. Do you get it? So I can pair this and multiply it down. Next number, negative 3 squared all the way down, negative P minus 1 squared. And total, how many negatives can you find in this third column? How many negatives can you find? 2k negatives, right? So if you multiply all these through, then it is equal to, will be equal to minus multiplied total 2k times, right? Total 2k times. And then 1 squared, 2 squared, up to P minus 1 squared, right? So if I multiply the left side, then we get this thing. Then take a look. Negative 1 multiplied even numbers is what? 1. So it is 1 times. I can extract the common power, 2 power, right? Then it is 1, 2, 3, all the way up to P minus 1 over 2. Right? I extract the power. I extracted power 2 and got this. Then let's go to the original position. What I did was multiplying all the numbers in these 2 columns. If I multiply all these numbers 1 through P minus, what is it? By Wilson's theorem, what is it? it is what? If I multiply up to p minus 2, then it is what? 1. But if I multiply 1 through p minus 1, then what is it? If I multiply the numbers up to this point, it is 1, right? I multiply all numbers up to this point, it is 1. But if I multiply 1 and negative 1, then what is it? Negative 1. By Wilson's theorem, this is congruent to negative 1, right? Then take a look. If I say x equals 1, 2, 3, all the way up to p minus 1, then the left side is 1 times x squared, and the right hand side. In other words, when p happen to be 4k plus 1 type, then it has a solution, and the solution is nothing but the product of 1 through p minus 2 or p minus 1 over 2. So I completely proved this case. So I proved both directions, right? If solution exists, p should be 4k plus 1, and vice versa. If p is 4k plus 1, then I can find the solution, and solution is nothing but this. So if someone asks you to find the solution to this, so example, if someone asks you to find the solution, x squared is negative 1, mod something, for instance, 37. I cannot think of big prime by my brain, so I just pick some number like this. Then what should you do? Multiply 1 through 37 minus 1 over 2, or 1 through what? This is 36 divided by 2, 18, right? So multiply these, then it is the solution. So let's do it. Product of 1 through 18, mod 13, right? Mod 13 is the result, right? Product of 1 through 18, mod 13 is the result, and then it is what? Mod 37, sorry. 31, right? 31. 31 is the result. Can you get this kind of number by just guessing? It's almost impossible. So let's check it. Mod 31 squared over 37, right? Then 36 o'clock is the same as negative 1 o'clock, right? So I proved the theorem, but not just proved, I gave you the solution. So whenever you are asked to solve this kind of problem for any prime, you can first check this odd prime is legitimate or not. So let's pick some prime and then check. Assume that you are asked so you may pick any prime in here. Pick any prime. What prime do you like? 83, right? 83 is a prime. Then if someone asks you to find the solution with 83, then what should you say? 83 is 4k plus what type? 83 is 4k plus what type? 4k plus 3, right? 4k plus 3, because 80 holds 4 times 20, right? 4 times 20 plus 3. That means it doesn't have a solution. It doesn't have a solution. How? Do you want to do computer search? You can do it. So let's check it. So 83 mod, I will run the program so that you can detect it. For I running from 1 through 82, right? 1 through 82. And then I will print out I squared, right? Mod I squared 83, right? And then I also print out I. So I will print out these things and then end, right? So check it. Do you see 82 anywhere? 자, take a look. Do you see 82? Because -1 with 83, our clock system is 82, right? So do you see 82 anywhere? 82 is nowhere, right? 82 is nowhere. Right? There is no 82. In other words, you don't even have to consider or try to solve this problem because mathematically it is proved there is no solution. 82 o'clock doesn't exist. Right? No 82 o'clock. So there is no negative 1. Why? Because 83 is 4k plus 3 times. Do you get it? If you don't believe, we can consider more. Do you want to go to the next topic or browse this more case?
One more.
One more. Then you may pick any number in this chart. I picked prime numbers here, so you may pick any prime here. Any? Excuse me?
53.
53. Then 53. So someone chose 53. 53 is equal to 4 times 13 plus 1. So it is 4k plus 1 type. That means it has a solution. Right? It has a solution. Then what is the solution? It is 53 minus 1 over 2. 52 over 2. Then it is what? 26. 26. We should multiply all the way up to 26. That's the solution. So let's do it. The major reason is the computer handling of integers. Computer cannot handle big integers. I break up 1 through 26. So from 1 through 10, mod 57, right? And then mod 11 through like 11 through about 17, 53, right? And then mod 18 through about 50, 26, let's be bold, right? 53. So I will multiply these numbers instead of multiplying at one piece, right? So I did it. And then now answer mod, this answer 53. Then it gives us 23. 23 is the answer. So let's check it. Mod 23 squared 53. 52. 52 is negative, right? So I showed. Any questions? So the answer is 23, and then 23 is nothing but the product of all the numbers up to 26, right? So the solution is 1, 2, up to 26 mod 53, and then mod 53 gives us 23, and then 23 squared. 23 squared is congruent to -1 mod 53. So he completely showed you this fact. So on the exam, I may give some problem, and you can solve.
You have a short
product of these kind of numbers, let me think.
26 would be very difficult to do by.
If the modulus is big, it's almost impossible, right? If the modulus is big. But if the modulus is not very big, then we may consider some other ways. So it's like this. If you are a biologist, then you may need a microscope, right? So if you are someone, then you need something. If you are studying number theory, you need computer. You need computing power. The next chapter is number theoretic functions. So it is chapter 6, number theoretic functions. What are the number theoretic functions? Some function having integers here, okay? Something having integers, especially positive integers, or sometimes people include 0 too. But no matter what, when you handle f of some integer function, then it's called number theoretic function. Usually function doesn't require it. For instance, it's a function, right? This is a function. But this x can be anything, right? X can be an integer, x can be anything. Of course, we can consider this as a generalization of number theoretic function. But we are not interested in this direction. We are interested in number theoretic function having integers, especially positive integers. Sometimes for convenience, people include zero. So let's do it. So first of all, we want to consider the case like this. Pick any number. Pick any number. 7. Then what are the divisors? 1 divides 7. 7 divides 7. Obvious. Then how many divisors can you find? 2, right? There are 2 dividers. Pick some other number. 18. Then 18 is divided by 1, 2, 3, 6, 9, 18. So how many divisors can you find? 6, right? So we can make a function indicating this number. So let's call this tau function. Tau function of n indicates the number of divisors, right? The number of divisors is called the tau function of n. So give me a number, then I can find the tau function of n. For instance, 5, then 1 and 5, that means 2. Pick any number. Tau of 24. Can you get it? 1 divides it, 2 divides it, 3, 4, 6, 8, right? 12, right? And then 24, right? Total 8. Total 8. So these are the cases, right? So number theory functions are functions of this type. And the typical case is the number of divisor function. So once you plug in positive integer, you will get the result. Of course, in other cases too, it's true too. But they are not just limited to positive integers. They are general. But here, we focus on integers. Now, the second function, it is called sigma function or sigma 1 function. So sigma function is the sum of divisors. Sum of divisors is called the sigma function. Because we picked some numbers upstairs, we recycle the numbers that we chose. First of all, sigma of 7. Then what? 1 and 7, 8. sigma of (18), then what is it? 1 plus 2 plus 3 plus 6 plus 9 plus 18, right? So 10 and then 30 together, right? And then 39. So you can do these things too, right? So these are number theoretic functions, and I'll explain the notation. This means sum of something, right? Sum of something. And this means product of something. And underneath, people write the condition. What kind of sum? What kind of product? So for instance, in short, people write this kind of notation. Sum of D dividing N of F D. So take a look. What does this mean? It means sum of F of factor of D, factor of N, factor of N. For instance, I will specify a number, 7. Then what does this mean? One number divides 7. One number divides 7. D divides 7. One number divides 7. 1. And then sum, right? This is sum. And then F of 7, right? This is the expression. In other words, instead of writing down this expression, we can use some expression. In this case, you don't see much advantage because the right hand side is simple enough. But assume that you have 1,000,000 here. Then is it possible to write down these kind of things? Or assume that you have billion here. Is it possible to write down these kinds of things? It's very difficult. So it has an advantage, right? This has an advantage. Do you get it? Then product. Product of D divided 7, FD. Then what is it? F1 multiplied by F7. So these are notation that we will use in the following sections. In this sense, we can write sigma function this way. Sigma of n can be written this way. Sigma of n is this n, right? This n written here. Do you get it? This n written here. And then f of f happened to be itself, right? F have the identity function, this, right? So the divisor, sum of the divisors. This is the definition in sigma expression. In other words, in the past, we used like verbal expression, right? Sum of divisors is the function, but now with this notation we can write it mathematically, right? In mathematical expression. Do you see the advantage? So let's do it. Sigma of, for instance, 7 equals D dividing 7 added, right? Then D, what divides 7? 1 divides 7, right? 1 divides 7. And then what divides 7 divides 7 and 8. Do you get it? So 1 divides 7. And then 7 divides 7. So 1 and 7 are added. What if I define this kind of thing, sigma 2 of 7, which is nothing but this thing but square attached, this 2 attached. Then what will be the result? This will be what? 1 squared plus 7 squared, 50. Do you get it? So we can do anything. Oh, let's attach 3. Let's attach 3. Sigma 3 of 7. Then D7, D cubed then 1 cubed plus 7 cubed, then it should be 344. Oh, I want to calculate sigma 0 of 7. Sigma 0 of 7 is nothing but d dividing 7, d to the power of 0. So I use d to the power of 0. Then 1 to the power of 0 plus 7 to the power of 0. 1 to the power of 0 is 1. 7 to the power of 0 is 1. And then 2. So we can define anything. So I will define sigma s of 7. Sigma s of 7 is what? Sigma s of 7 is 1 to the power of s, 7 to the power of s. In this sense, tau is nothing but sigma of 0. Do you get it? Tau is nothing but sigma of 0. Why? The number of divisors. The number of divisors are counted here, right? 2. So we can define many things using this notation, and I chose a very simple one, but it can be very complex, right? This can be very complex. Assume that the number is not 7. Assume that the number happened to be 24. Then it's way harder. So I explained the introduction and notation part, and if you don't have any question, then I will cover a very, very important fact. Then let's do it. By the fundamental theorem of arithmetic, we can write down this kind of thing. Oh, 24 is equal to 2 to the power of 3 multiplied by 3, right? 8 times 3 is 24. So we can write it this way. So by the fundamental theorem of arithmetic, we can write it. Then, in this sense, the divisors are a combination of these powers. So take a look. 2 can vary from 0 to 3 power. Do you get it? 0 to third power, right? Zeros to the third power. 1 can vary from 0 to first power. Do you get it? So the possible powers for 2 are these things, right? Possible powers for the 3 are these things. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 3 to the power of 0, and so on. So we can have these things. Then we can create divisors of 24. What are the divisors? Any pairs. So for instance, this pair, right? This pair is a divisor. And we can just take any pair. This is a divisor. Then, if we count, how many divisors can you find? If you count, how many pairs can you make? 8, right? There are 8 divisors. Do you get it? There are 8 divisors. So this is the idea. And all the divisors have this pattern. Then the next thing, with this, if we are equipped with this, then we can write a better result. First of all, tau of n is not that complicated if n happen to be p1 and then power 1, p2 power k2, and so on. And then the last number is pr and then power r. Assume that we have this kind of decomposition, then we can make how many for each power? For each power, how many can you make? Assume that we have 3. In this column, how many could we make? 4, right? Assume that we have 1. How many could we make? 2. So, for this k1 power, how many can you make? For this k1 power? k1 plus 1. For this k2, how many can you make? 8 plus 1. And then all the way up to kr plus 1 in each column. And then we can make any r tuples, right? Any r tuples. We can make any possible r tuples. So these are the possible numbers. Now, if we want to find sigma n, then we should do these things and then add. But instead of adding after multiplying, we can add in this column and then multiply together for convenience. Do you get it? Instead of adding these things column after multiplying all the way and then multiplying all the way and then multiply all the way, we can just add each column and then multiply these things together. Do you get it? This is the idea. So if I want to add the numbers, then we just multiply each column. So P1 to the power of 0, P1 to the power of 1, up to P1 to the power of K1. So I add the column. Instead of later adding this column, we just add. Do you get it? And then P2 to the power of 0 up to P2 to the power of K2. And then multiply by PR to the power of K0 up to 0 up to PR of KR. So we can add the divisors this way. If you doubt it, you multiply this out. If you multiply this out, then P1 to the power of 0, P2 to the power of 0, all the way to PR to the power of 0 written down. That is 1. That is a divisor, right? Plus P1 to the power of 1, and then anything, right? P2 to the power of 0, and so on. And then add. That is also divisor of n, and so on, right? So we, instead of adding individually later, we just compactize these things in each column and then multiply. Instead of multiplying and then add, we reverse. We add and multiply. Do you get it? So this is the idea to get the result. So with this, now I can handle the problem such as this thing. Oh, find 18, right? Question was finding this thing, right? Question was finding this thing. Then, oh, it is product of 3 to the power of 2 and then 2 to the power of 1. Then for 3, we have 1 or 3 to the power of 0 to indicate the idea. 3 to the power of 0, 3 to the power of 1, 3 to the power of 2, multiply by 2 to the power of 0, 2 to the power of 1. Then it is 1 plus 3 plus 9. And then this is 1 plus 2. Then the left side is, this left factor is 13. This right factor is 3, 39. Or if you don't like it, then you can write it. So I will multiply through. This multiplied together gives us 3 to the power of 0, 2 to the power of 0. And the next gives us 3 to the power of 0, 2 to the power of 1. And the next gives us And the next gives us 3 to the power of 1, 2 to the power of 0, 3 to the power of 1, 2 to the power of 1, 3 squared, 2 to the power of 1, 0, 3 squared, 2 to the power of 1, right? So instead of multiplying and then adding, we add it and then multiply. This is the key idea. Do you get it? Instead of just multiplying and then later add, we reversed. We added each column and then multiply. The result is the same. Then can you generalize this thing for any case? And there are some cases that we can do it. So that is very, very important case in this number theoretic function handling. This is the very, very important one that you should remember. But if you have a question up to this point, ask me, because the next thing looks abstract, but it's not very abstract. I will show you the reason. Any questions up to this point? The next thing is, if this is very important question, greatest common divisor of m and n is 1. In other words, if they are relatively prime, what kind of case, right? For instance, 125 and 81. Then are they relatively prime? they are relatively prime, right? In any case, if this happens, then f of m multiplied by n can be written in this form. So assume that this kind of thing is satisfied, then we call this function f multiplicative. So it sounds abstract, but it's not very abstract. In other words, when you have f of mn, when mn are relatively prime, top one is the key. If they are not relatively prime, then we don't care. For instance, 2 and 4 are not relatively prime, then we don't care. But if they are relatively prime, then we can decompose. In other words, if it's multiplicative, then f of 125 multiplied by 81 can be handled by knowing 125 and then 81. Do you get it? If it's multiplicative, but if it's not, then you don't care. Right? There are many functions which are not multiplicative. So we are handling very limited set of functions. Instead of all functions, we are handling limited set of functions called multiplicative functions. What? When they are relatively prime, then this. Then take a look. If a function is multiplicative, if f is multiplicative, is this true or not? If f is multiplicative, then is this true or not? Is this true or not? Not. Why not? That's right. GCD of 24, 18 is not equal to 1. In other words, even if f is multiplicative, we don't have any guarantee that we have this kind of expression. Only when these two numbers are relatively prime, we can get this kind of result. Do you get it? So even if f is multiplicative, we cannot just decompose this way. Then how should we decompose? How? We should decompose by this idea. Assume that n is equal to p1 to the power of k1, and then pr to the power of kr, and multiplicative, then f of n or p1, k1 all the way up to pr, kr. Then what can you say? F of p1, k1, and then multiply all the way through pr, kr. And this is the very, very important key. Why? Because if it's multiplicative, then all you need to care is not the number in general sense, but just the factor. In other words, just the factor with the highest prime is your major concern. Then there is a limited number dividing. There is a limited number of elements dividing p1 to the power of k1. So p1 to the power of k1 is divided by what? 1. Can you find another number? p1 itself divides it, right? Can you find another number? p1 to the power of 2, right? p1 to the power of 3. Can it go forever? No. p1 to the power of k1. These are the only cases. Do you get it? If the function is multiplicative, then you only care about the factors. But what factors? Prime factor. For each prime factor, there are not very many divisors. There are only limited number of divisors. Total, how many can you count? How many can you count? In this case, how many can you count? How many divisors can you count? I mean, number of divisors. How many divisors can you count here? For this number, it is divided by how many numbers? K plus 1 numbers. We did it before, right? When we did the column calculation. So let's go up. When you did the column calculation, when you have 2 to the power of 3, how many divisors of 2 to the power of 3? 2 to the power of 0, 2 to the power of 1, 2, 3. So the total 4 numbers divide 2 to the power of 3. What about 3 to the power of 1? 2 numbers. Same way, possible here. Right? When you have p to the power of k1, then we have total k1 plus 1 number. In other words, we don't have to worry about very many numbers, only 1 through this number. Then it is way easier in calculating the number. So using this fact, we can show many, many things. So these are the things that we need to do. I will pause and then write down the strategy. First of all, show f is multiplicative. So we need to show that the function given by the problem is multiplicative. Second thing, prove this case for prime power. P prove the case for P S R KS, right? KS, right? Prove the theorem or something for PS, KS, or if you don't like subscript, just P to the power of K. This is generally enough, right? Prove the case, prove the statement for this. Then after this, what should you do? You just multiply these cases, right? You multiply these cases to prove the case. So we will, when you are asked to prove it, you need to prove it, or when you are asked to calculate it, you should calculate, right? So either prove or calculate for not very general case, but for a specific case, having limited number of divisors. This is the key. So I will pause and then you can check and ask. If you don't, then about 4-5 more minutes, I will give you examples. Any questions? You don't? Then next time, I will give you examples. First of all, tau is multiplicative, and sigma is multiplicative. Sigma 2 is multiplicative. Generally, we can call this sigma 0. We can call this sigma 1. Sigma 3 is multiplicative. And then sigma s is multiplicative, right? So these are multiplicative functions. And there are other more important multiplicative functions that I will introduce down the line. But these are the cases. Then what will I do next time? If f of n is multiplicative, then will the sum where n divides, for instance, capital N, multiplicative? And it is true. So I will prove this case next time. But I'm introducing the direction. So next time, on Wednesday, I will prove that if f of n is multiplicative, then this kind of sum of multiplicative functions is also multiplicative. It's not very difficult to prove. And the reverse is also true. If the sum is multiplicative, then this function f also is multiplicative. So the other way is also possible. And then I will introduce some important functions connecting. Let's name this, because I said sum, but let's name this. So sum function, right? Sum function of n. Then if you have a sum, then if you have f, we can get a sum, right? This direction is obvious, right? If you have a sum, if you have a function, then we can have a sum. It's obvious direction. Do you get it? It's obvious direction. The other direction will be studied. If you have a sum, then you will have a function. The other direction, called inversion, will be. So next time, I will cover these things. But because today I have covered many things, I don't want to cover any new things. But if you have a question on anything that I covered today, ask me. Ask me right now or ask me personally. So let's stop here, and then you can approach and ask.